In this section, we're going to talk about some of the rules and methods that we use to calculate probability of compound events. So to start, I want to go over some definitions. So in an event that includes one and only one of the outcomes for an experiment is called a simple event. And these events are usually what we've been working with from the previous section. And a compound event is an event that is formed by combining two or more events. So we're gonna talk about two kinds of compound events, A or B and A and B. And when we talk about the probabilities, we denote it as the probability of A or B and the probability of A and B. And one way that we could compute this is using something called a contingency table. And they're really useful when computing probability of A or B and probability of A and B. And we're going to talk about a simple example of a contingency table. Let's consider this partially filled contingency table. So suppose all 100 employees of a company were asked whether they're in favor or against a certain policy. In order to fill this out, we want to know the total number of males, which is adding the total number of males who are in favor plus the total number of males who are against. In this case, it's 60. We do the same thing for female, which is 4 plus 36, which is 40. And you do the same thing with the total number of people who are in favor and who are against. And if you take the total sum, either rows or the column, it should give you the same number, which is 100, which makes sense because there was 100 employees, so that's one way you could check your answers. Next, we want to select a random person from this group and find the probability for each simple event. For example, the probability of picking a male out of this group will be the total number of males over the total number of people working in the company. And again, we do the probability of picking a female, which is the total number of females over the total number of people in the company. And the probability of people who are in favor of the policy will be the total number of people who are in favor over 100. And again, the probability of picking a person who are against is the same thing. Next, we want to find the probability of a person who are in favor and who's a male. If you look at the consistency table, you look at the column in favor and the row of the male and see where they intersect, which is 15. So the probability of a person who's in favor and a male is 15 over 100. Or another way you could think about it is the number of male employees who are in favor over the total number of people who work there. And again, if you want to find the probability of a female and who's against the policy, you look at the female row and the against column and see where they intersect. And they intersect at 36. So this will be 36 over 100, which is 0.36. So finding probability using a contingency table is pretty simple, especially when we're dealing with probability of A and B. But notice that we haven't done any example with the probability of A or B. For that, we're going to use a different method. So we use something called a general addition rule. So if A and B are two events, and we want to calculate the probability of A or B, so this is taking the probability of A and then adding the probability of B and then subtracting the probability of A and B. So let's consider the table that we did earlier, and we want to know if we select a random person, what is the probability of that person to be in favor of the policy or a male? If we follow the formula, this is just the probability of I plus the probability of M minus the probability of I and M. But we already calculated these values already. If you look up here, the probability of a person who's in favor is 0.19. And the probability of getting a male, if you look up here, it's 0.6. And then we're subtracting the probability of I and M, which is 0.15. So we already calculated these values, so all we have to do is compute it, which is 0.64. Next, we want to know if we select a random person, what is the probability of that person being a female or against a policy? And if you look at the formula again, this is just P of F plus P of A minus P of F and A. But again, we already know these values already because we computed it up here. So all we have to do is plug in the numbers. Once you plug in the numbers, you want to compute the value, which should be 0.85. And this just means that if we select a random person, the probability of that person being a female or against the policy is 0.85 or 85%. So just a little bit of review. So if we pick a random person from the 100 employees, and we want to know what is the probability of that person being in favor of the policy or who's a male, we have to use the general addition rule, which is just the probability of a person who are in favor plus the probability of the person being a male minus the probability of that person being in favor and who's a male. And we already computed these. We just plug in the numbers and we got 0.64. So another way of saying this is that the probability of we randomly select a person, and if that person is in favor or a male, is 0.64 or 64%. And we do the same thing for this example. And another thing I want to talk about is something called mutually exclusive. So mutually exclusive just means that if A and B are two events, it is impossible for both of the events to occur at the same time. So that's what it means to be mutually exclusive. Another way of saying this is that the event A and B have no outcome in common. So what does this do? So if your probability of A and B is 0, so you conclude that they're mutually exclusive, because this is saying that A and B have no common outcome. So if you calculated this, and if this is true, then they're mutually exclusive, event A and event B. So what does this do with the formula? What does this do with this formula here? Well, if this is 0, then if two events are mutually exclusive, we have the probability of A or B is just going to be equal to the probability of A plus the probability of B, because this part here is going to be 0 since they're mutually exclusive. So that kind of changes the formula a little bit. Let's do some examples with mutually exclusive, and let's consider the table that we've been working on. We want to know whether these two events are mutually exclusive. So selecting a male and who are against the policy. One way to figure out if they're mutually exclusive is to compute the probability of M and A. If this is 0, that means that M and A are mutually exclusive events. And you look at a table and you look their intersection, which is 45. So this will be 45 out of 100, or 0.45. And notice that this is not equal to 0, which kind of tells us that M and A are not mutually exclusive events. And again, the reason why is because when we calculate the probability of M and A, it gives us a value which is not 0. It has to be 0 to be mutually exclusive. Next, we want to see how this affects the general addition rule. To calculate the probability of M or A, using the general formula, we know that this is just the probability of M plus the probability of A minus the probability of M and A. But we already know these values, so all we gotta do is plug in the numbers. And since the event M and A are not mutually exclusive, the probability of M and A has a value. So this will be 0.96. So let's consider this example. We want to know if in favor and against are mutually exclusive. So we compute this. And you want to see if it's equal to 0. If it is, then it's mutually exclusive. Looking at the value, the columns in favor and against have no common intersection. So this kind of tells you that there's no outcomes that are in common. So when this happens, we could say that these two things cannot happen at the same time. So by definition, they are mutually exclusive. So we could say that the probability of I and A is 0. So you want to see how this affects the general addition rule. So to calculate the probability of I or A, so this is the probability of I plus the probability of A minus the probability of I and A. But since we already know that I and A are mutually exclusive, we know that this will be 0. So all we have left is the probability of I plus the probability of A, which is what we expect. And if you plug in this value, we actually get 1, or 100%. And this makes sense because when you pick a random person, they're either going to be in favor or against the policy. So they're either one or the other. Let's do a couple more examples about mutually exclusive. Oftentimes students have a little bit difficult grasping this concept, so I want to do a couple more examples. Let's consider a standard deck of cards. A standard deck of cards are just 52 cards with 4 suites: spades, hearts, clubs, and diamond. And each suite has about 13 cards, ace all the way to king. And we want to know the following are mutually exclusive events. So let's consider R as in drawing a red card, and event B, which is drawing a black card. Can these two happen at the same time? So the answer is no. We cannot pick a card, a random card, and having that card to be red and black at the same time. So we could say that these two events are mutually exclusive. Another way of saying that is that the probability of R and B is equal to 0. But let's consider another example. So we have two events, drawing hearts and drawing a king. And well, in a standard deck of cards, there actually is a king of hearts. So there is a king of hearts. So these two events can occur at the same time. Thus, they are not mutually exclusive. So given these kind of problems, you want to think whether can these two events happen at the same time. One thing I want to talk about is something called complementary events. And what complementary events are, let's say I told you that there's going to be a 40% chance it's going to rain tomorrow. But what if I ask you, what are the chances that it's not going to rain tomorrow? It's 60%, right? It's the opposite. So that's kind of like what I like to think when I think about complementary events. So by definition, let's say E is any event of an experiment. So the complement of E, so we call it like E to the power of C. So this is denoted as E complement, is all of the final outcome that is not the outcome in event E. So it's the opposite. And there's a couple properties that you want to know about this. So we know that the probability of E plus the probability of E complement is always 100% or 1. Think about it like this. If the probability of it going to be raining tomorrow is 40%, and the probability of not going to be raining tomorrow is 60%, well, you know that 40 plus 60 is 100%, or just 1. And let's say you know one but not the other. So let's say you knew about the probability of E, then you could calculate the probability of E complement by just taking 1 minus that probability. And same goes for the probability of E. Let's consider some examples. So here, suppose we flip a coin 3 times and we want to determine the sample space. I would actually recommend you pausing the video and kind of do this on your own, just for practice. One way we could do this is use a tree diagram. So for example, on the first flip, we have heads or tails. And on the second flip, we have heads, tails, head, tails. And on the third flip, we kind of do the same thing. Then we want to follow the line, and then that will be our outcome. So this will be heads, 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 and then heads, heads, tails, head, tails, head, and then you keep going with the pattern. Once you finish, we have to put it in set notation. So we have S and then curly bracket, and you put all the possible outcome, and you close it with another curly bracket. And once you finish, you have successfully determined the sample space of a coin if you flipped it 3 times. So these are all the possible outcome. Next, you want to find the outcomes of A, where A is the events that are exactly 2 tails. And if you look at our sample space, that only happens 3 times. So this is HTT, THT, and TTH. So you list them here. So this is your event A. And then finding the probability of A will be 3 over 8, which is 0.375. Now you want to find the list of outcome in A complement. So A complement are just everything outside of A. So it's everything that does not have exactly 2 tails. And that happens in 5 different events. So the probability of A complement will be 5 over 8, or 0.625. But there's another way. If we know the probability of A is just 0.375, then the probability of A complement will be 1 minus the probability of A. So if you compute this, this will give you exactly the same number as what we did earlier. And notice that they're the same. So according to the Wall Street Journal, 40% of cars sold in recent year were really small cars. And we want to know what is the probability that a random chosen car sold in that year is not a small car. So this is kind of the example of the rain and not rain. So it's going to be 60%. Another way you can think about this is just 1 minus 0.40, which gives you 0.6, but this is just 60%.